Alrighty, thank you, Jess. So basically, this is where idea comes in. We already talked about Strut and Tide, so we'll see where idea plays into this role. So in Idea Statica, we developed a software solution that's specifically able to handle all of these regions. So it's built around a method which we call CSFM, which is basically the compatible stress field method, and it allows you to calculate, design, and detail all of these key regions. Here, the app, since it's not linear analysis, it uses um, the assumptions that basically concrete does not act in tension and that all tension must be transferred by the reinforcement. So if we look at the screen from left to right, you can see how this workflow will play out. On the left-hand side, we have the strut and tie column, and this is basically the kind of hand sketches that every bridge engineer might be familiar with. If we shift to the right, starting in the middle, this is where all of this will translate into the model in our detail application. You will be able to define the geometry, the loads, the support, and the reinforcement. From there, the design tools column, this is where you will be able to see the resulting force flows, the struts in compression, and the ties in tension, which is very similar to what strut and tie method does. Finally, on the right-hand side, this is where we're able to see the results. We're able to see the strength stress results for both the concrete and the rebar. And so basically this allows you to verify that everything checks out against the code. Now, these capabilities that have been shown are not the only type of capabilities that are allowed or able to be done within detail. And that's because CSFM is based on, again, nonlinear analysis. And two of the most important additional capabilities are for serviceability checks. On the top, we have deflections, and this is basically where the software calculates both short-term and long-term deflections directly within the model. At the bottom, we do have crack width, and again, within this serviceability check, this is often a heading to be able to do this by hand. Basically here with CSFM, you can see exactly where the critical cracks are and whether they're within those allowable limits that might be set by your code, agency, or the different states that you're working with. Now, let's take a look at a real world example on how this detail application gets used in practice. So here, Detail 2D has been part again of in Idea Statica Suite. Detail 2D has already been part of our applications for a while now, and some engineering firms have already been using it for different projects. Now here for this example is from IMEG, and basically they use Idea Statica Detail as part of a peer review on a project involving walking columns. Within this project, they compared results against ACI 318 within their Strut and tie hand calcs, validating the software against basically code-based approach and being able to verify their flow forces for the model. Here you can see the results on the right with the strength and serviceability checks for all of them, whether it's a concrete reinforcement or the anchorage. You can also see the stress fields clearly visualized from the column floor column transition. And in case you're interested in reading the full article about it, it will be linked in the PowerPoint presentation. And again, as a reminder, it is already available in the webinar for you to go ahead and grab it. Now, let's go ahead and talk about the AASHTO bridge design specification. Like other concrete codes, here the AASHTO specification offers guidance on the strut and tie method for all of these D regions, specifically for concrete bridge substructures. All of these structures that cannot be designed using the general beam theory. So here, if an engineer decides to go through the strut and tie method route, what AASHTO does is they provide them through um, they basically walk them through the different steps. So basically, it helps them construct the model, apply the material, design the zone factors, and once the forces are calculated, they can then start detailing the reinforcement. Now, this is the traditional path and it works, but again, it can be time consuming with the different iterative approach by trying to find the right iteration. Now, this brings us to our big news that we have for today, and that's with starting with version 26, Idea Statica is now officially ready for all of these infrastructure concrete details because now it is fully implemented with the AASHTO code. So all you have to do now is, well, whenever you open the Idea Statica application, you can pick the AASHTO code directly and select from our different templates of bridge substructures to be able to help you get started. So once you select a template, these templates will come preloaded with everything that you will need. So those things include the AASHTO material models, the stress strain diagrams, the resistance load factors, and the different load combinations. Now here on the slide, you can see the full scope of what is covered within our application, but the best way to really see how this works is really to go through a real example. So from here, I'm going to hand it over to my colleague Andrea, who's going to walk us over through an example, which is an inverted T moment frame straddle bend cap, which will be modeled and designed in detail 2D using the AASHTO code. So Andrea, over to you now.
All right, so thank you, Johan, for the intro. Now let's jump into an example that I prepared for this session. This is an example from the National Highway Institute training book that it's called Strut and Tie Modeling for Concrete Structure Design Examples. Here is the reference. You can find this in internet and download the PDF. In this case, I'm presenting the third example in that book. And it is an inverted T bend cap beam, which is part of a moment frame straddle bend. This beam will carry a flyover ramp over a highway. So here you can see the elevation and then the plan view. So in the next slide, you will see a picture of a similar structure. In that design example, they explain the process of using a strut and tie method in the global model of the beam. And then they also use a local model for the cross section at the beam ledge. The beam section changes from rectangular to an inverted T along the length of the frame. So you can see it here in the plan view. And if you look at this picture, also you will see a similar structure where there is a rectangular cross section and then it changes because we need to carry these girders here and then you'll have some reactions on this ledge, right? So because the section changes and you want to see the stress flow on those ledges, we need to create a local model of that cross section. So in the example, they do that strut and tie model for that cross section. And then in detail to the application, we're going to do a similar approach. Okay. Now let's review the loads in the example. So the self weight is calculated as a linear load. So they provide this information. And also they provided factored beam reactions at the ledge. Okay. So you can see beam line 1, 2, and 3. So we have 3 beams coming in into this side, another 3 beams coming into this other side. So in our case, in the detail application, the self weight can be calculated automatically. And then once you apply the self weight for the load for the strain load combination, we need to multiply that self weight or that dead load by a factor. And we're going to use 1.25 per AASHTO. Then, because we're going to use the factored beam loads, so we don't need to add a factor. They already have that factor included in the total load here. So we're going to use a factor of 1 only, okay? And then in this slide, I am presenting the step-by-step process. So you can follow along as I am presenting in the software. But in general, you go from modeling the structure, modeling the supports, load cases, and load combinations. And then in detail 3D, you first run a linear analysis we call topology optimization. That will help you to see the stress flow without considering reinforcement. So it will be kind of an initial calculation. And then with that information, that will resemble to an strut and tie stress flow. With that information, you can start the pre-design of the steel reinforcement. In detail application, we model the reinforcement as you can see here. You model the longitudinal rebars and then the stirrups, and then we can run a nonlinear analysis. So that nonlinear analysis will consider the concrete elements and then the reinforcement at the same time. Okay. After that, after you verify utilization ratios and then deflections and crack widths, then and everything is passing, then you can create the report. So you will see this process in the application while I'm doing that demonstration. Okay. So I prepared three models. The first two models that you see here, they are the global model of the beam. So I model two options because in detail application, you can model as a beam element and you will see how I model that. And also you can use this wall element. It changes in terms of simplification, and then also there are some options in the beam element that it's really easy to model stirrups and their reinforcement. But anyway, you have the two options, and I wanted to show these two options that you can follow. And then finally, the third example is this section of the ledge beam, right? That will help us to design the shear reinforcement for this section. Right? So now let's jump into the software and let's review the process. All right, now I am in the Idea Statica launcher, and then as you can see here in the top right corner of the launcher, you will see the version. Now I am in version 26, and then I'm going to focus today on the detail application. So I'll click over the detail icon. All right, so now we are in the wizard of detail application. So from here, I'm going to start with the 2D version. Essentially, the difference between these two is the finite element model that we are using. For the 2D, we're using shell elements. For the 3D, we're using 3D block finite elements. We're going to use the 2D for now. And then once you're here, go directly to this design code. And here you can see I have the ACI code. If you click over the drop-down menu, you will see the new AASHTO code. So once you change to the AASHTO code, you will see these sample projects that we were mentioning before, specifically for bridge substructures, right? But today I'm going to use the general option, and that is basically starting from scratch. Okay, I'm going to change the material default settings here. So I'm going to use 6000 psi and then grade 60 for the seal reinforcement. I'm going to hit OK and then create. Now, this is the detail interface, and if you have used Idea Statica Connection, this is a similar interface. So at the top bar, you can add new items. So I'm going to hit New Model Entity, and then here you'll select what type of element you want to use for this model. So as I was mentioning, there are two options between wall and beam. There are some differences between the modeling. So I'm going to start demonstrating how to use the beam elements here in detail. So one of the advantages of using beam element is that we have preloaded some sections, some common sections. So for now, I'm going to use the rectangular shape. And then here we're going to give the dimensions that we have. So this will be 60 inches, and then this will be 40 inches. And then I hit OK. So this is creating that beam section. We're looking at the 2D view, but we can change it to the 3D model view. So that will be easier when we are constructing this model. If we look at M1, that is the new member that we create, we can input this length over here. The first portion where the beam is a rectangular cross section, the length is 17.59, so let's change that. Now let's add a new member. So that new member will be another beam. So now if you see, here we have the options specifically for beam elements, okay? So anyway, I'm going to add a new beam. This second beam that I added it will have a different cross section. That will be the inverted T section. So to change the section, just go ahead and click over the plus icon. I'm going to use this inverted T section, and then let's give the details of that new cross section. I'm going to actually copy M1. So I copy that M1. It will have the same rectangular section that will have a length of 5 feet, and then that will be located from M2. And then from master point 2, and then insert point should be 1. There you go. So now we have the different cross sections along the beam. Now let's add the supports. So for this, I'm going to hit new model entity. And then here we have some supports options. In that presentation, I have some links to learn more about the supports. But I like to use the point distributed because you get one value for the reaction. So it's useful when reviewing results. The support size will have the same size as the beam. So let's locate it correctly here. So it will have the same size as the column that will be supporting this frame, right? So I'm going to just copy this support and I'm going to put it in under now M3. So also let's select what degrees of freedom I want to restrain. I'm going to free the X degree of freedom in one of the supports, and then I'm going to restrain C and RY. So that's all for the supports. And now let's jump into the load cases. So you click over the new load case. Now this new load case will be the permanent load case. In this permanent load case, I'm going to add the self weight. So clicking over new icon, then self weight, and that is applied to all the elements in this model. And then I'm going to add a new load case, and that will be the transient load case. In this load case, I'm going to add the reactions of the beams into the T section. In this case, I'm going to use line load. So what I'm going to do is I'm going to get the reaction, the total reaction in the 3 different beam lines, and then divide that reaction in the length of the bearing path. So that's how I'm going to calculate the line load, and I'm going to locate it here at the top of the ledge. Okay, so line load, and I'm going to add the first beam line. So that will be minus 186 minus 186.35. This will be on member M2. And instead of setting up from the H, I'm going to select points. So you can select it from different points within this beam. Okay. Right. So I added the 3 beam lines reactions. Now let's add the load combinations. So you can see that this first load combination is in this C1, and then you can select if this is a strength load combination or serviceability. For now, I'll start with the strength combination. Let's change the factors for the permanent load. So I'm going to use 1.25 per AASHTO, and then remember I'm using a factor of 1 because we have the factored beam load reactions. Click OK. And then now I can add a new combination. This new combination, this will be a serviceability combination. And then you can see that once you change it to serviceability, you can activate this combination for crack with check and deflection check. Usually we use a factor of 1 for all the load cases, but for the beam reactions, I have to reduce that because the factored beam loads that were provided. So 1 divided by 1.75, that gives us 0.57. So I'm going to hit OK. And then now we have this combinations, supports, and then the model. Per that step-by-step process, the next step is to run a linear analysis. So that means a linear analysis without reinforcement. So to do that, you can use this Tools tab, and then here we have this topology optimization. So let's click over it. Let's review the results. So the calculation uses an effective volume of the structure, either 20, 40, 60, or 80% of the volume or the material volume, right? And within several iterations, places this volume in a way so the created topology is as stiff as possible. The resulting shape consists of trusses with struts and ties and represents the optimum shape for the given load cases. Red color means compression, blue is tension. This can be used not only for the efficient reinforcement design, but also for creation of the strut and tie model if you wish to compare or verify the approaches, right? However, it's important to note that in this case, the self-weight was applied as like in an automatic way, right? If you want to compare this to the strut and tie model that it's in this example, it's not going to match exactly just because we are applying the self-weight in an automatic way. In this model, they apply the self-weight as reaction together with the beam reactions, right? So it won't match exactly. However, if you see the dashed lines here represent the compression lines, let's say, the struts, and then the continuous line represents the tension. Okay, so if we go back to our results, you can see the compression red line at the top. So it will be something similar, but if you want to match and you want to verify your strut and tie model, you should add or apply the forces exactly as you have it in that model. Okay, this is just kind of a quick note. All right, so once you learn how is the stress flow, remember, without considering the reinforcement, then you go back to the design tab, and now you can use that as an initial pre-design of the reinforcement. Okay. Now, to add reinforcement into this model, you just click over this new rebar assembly, right? And then for the beam elements, you'll have these three options. These other options, they are grayed out because maybe they are for other type of elements. In this case, when you select beam element, you can just select these three options, okay? So I'm going to start with the group of bars. And then let's change this view to the 3D real view. So this helps us to see what we are adding into this model. So let's change the definition of the diameter because this will be the longitudinal rebar. I'm going to change it to number 11 bar. Then the type of anchorage at the end of these beams will be a hook of 90 degrees. And in this case, it's just applied at the bottom part of this M1 member, okay? So then I'm going to change this number of bars in that layer, and that will be 6. I want 6 bars in that layer, and then you can change the number of layers, like if you want 3 or 4 layers, so you can see how they are being added there. For now, I'm going to just use 2, and then the distance between them is going to be 7 inches. Okay. However, I want this longitudinal rebar to go along the entire model. So I can use this option. So the end position of that rebar, you can define it using this length. Right, so that will run all across the entire beam. Right, so it's really easy to add this longitudinal rebar. I'm going to show you how to add an stirrup just for the demonstration. So I'm going to click over a group of stirrups. And then this is one of the advantages of using a beam element, because here you can automatically select the number of diameter, like the rebar for the diameter, and then you can select the type of stirrup that you want to use. If we look at this view here, you can see that this is a two-legged stirrup. It can be 3, 4, and then you can define the spacing between this. So for the first group of stirrups is going to be from M1 beginning, so 6 inches from the start, and then I'm going to start setting up, I'm going to add 28 stirrups multiplied by the spacing. So that will be 28, and the distance between them, they'll be 7 inches, okay? And then you can just copy this stirrup setup, and then starting from M2. Right? And then you can change the, in this case, I want to use 4 ledge stirrup for the T section. And then I'm going to start with 39 multiplied by 5. So the spacing of the first 39 stirrups will be 5 inches. And then I'm going to place 15 stirrups with a distance of 6 inches. Right? So it's really easy to add these stirrups when you have all right, so this is how it looks. This is how the model looks. I also added some skin reinforcement, so that's basically for to avoid any cracks, right? Um, to visualize these rebars, you can uncheck the draw option of rebars, and then every time you select a new reinforcement, um, you will see it here on the screen. Okay, so that is the modeling part for the beam element. Now I'm going to show you how to model it using wall elements. Now for the wall type of element in detail, let's hit new model entity. I'm going to select wall option. And in this case, there is no option to select a cross section. We can give the cross section using this width, height, and thickness, right? The thickness will be the dimension in the screen direction. So our first element will be the first rectangular beam. The width is going to be 17.59. The height is going to be 6 feet. And then the thickness is going to be 334, right? So the difference between the beam and the wall element is that in this case, we will need to create different blocks to create that T section. Okay, so after modeling the wall elements to create this structure, I followed the same process as I did with the first model. So I modeled the supports. Now they are at the end of the columns. In this case, I could model transfer devices. If you see, if I click over the model entity option, now we have other different types of elements to add. So in this case, I could add that bearing plate to be able to put the beam reactions as a point load. So you can see that I placed 3 base plates, and then if you see on the load cases, first load case is self-weight, then in the second load case we have this point load, and similar approach that I did on the other model. What will change is when we create a new rebar assembly. In this case, we just have the option to add group of wires and wire fabrics. So there is no automatic way to create the stirrups that we were creating before in the beam element. However, it's doable. You can mimic the stirrups using that group of rebars. So if you see, I'm going to activate the different reinforcements that I added, right? So what is the difference from this type of model and the beam elements? So in this case, I believe it will take you a little bit more of time modeling all those walls, creating like the ledges and all the elements in this frame. However, instead of creating a support at the end of this beam, as I did in the other model, we are actually model the column. So you will have a more realistic distribution of stresses and of course distribution of moments. So in my opinion, this is the best way to model this frame. However, if you want to do a very quick analysis, a very quick pre-design, you can use the beam elements and probably you will save some time. But you have two options to do this. Okay, so now let's jump into the results after we run the analysis for the both models, for the beam elements and then for the wall elements. After the analysis finish, we can come into the check tab. And then here's where we are going to look at the results. Here's a summary. For the strength combinations, we're going to look at three limit states: concrete and reinforcement strength, and then the anchorage. The anchorage can be translated to what we know as development length, right? So if you design concrete, you know that you need to calculate this certain length. So you know that the steel reinforcement is well anchored to the concrete. In this case, in Idea Statica, because we're using finite element analysis, we're calculating the bond stresses on the rebar, and then we compare it to the bond strength. So we don't really have to calculate the length, but we look into the stresses. We do similar with concrete and reinforcement. We calculated the stresses on the concrete, compressive stresses on the concrete, and then we compare versus the strength of the concrete that you pick, multiply by a factor. And these are the factors that we implemented for AASHTO. You can review them here under settings, and then you can see this tab that says AASHTO, and then you can see the different articles here. But these are the factors for the different materials. So this is for concrete, then this is for steel reinforcement, and then this is for pre-stressing. So you can look at all these different load factors that we added and some other details from AASHTO. Okay, so if you need to change some of this, you can come always to this project settings and change it here. Okay, so again, we compare the stress calculated in the model due to the applied loads and then compare to the reduced strength of the material that you selected. This is a first overview of the stresses in the structure. The red color is representing the utilization ratio in the concrete. So you can see here FC versus FC limit. The blue color is representing the stresses, well, the utilization ratio on the steel reinforcement, and then the yellow color is the anchorage results. So those are the bond stresses versus the bond strength. And also here you will see a summary of these results with the values. Okay, so this is kind of the summary of results. Then you can jump into the strength tab, and then you will see specifically the concrete results. So here we have different buttons that you can change. These are this is showing the utilization ratio, so you can see some color contours in this case, or you can change it to the stresses, like the compressive stresses. Okay. So one thing that I like to do is to change the name of the wells that I model, so I know where these numbers are related to what member, right? So you can click on these different elements, and then you'll see an isolated view in this area. Now, if we click over the reinforcement tab here, similar thing. I rename it the group of bars, so you have a detail results. So you can see at the maximum stress on that group of bars. Then you can see the utilization. So if you click over the different cells, you will see the maximum utilization ratio that is on the skin reinforcement. So then you can change on these different groups and see more results. Also, you can change this these graphs in the main screen. So here we're looking at the stresses, okay, and then you have the contours here. You can also look at the strain, okay. Similar with anchorage. With anchorage results, so you can click over this, and then you'll see the utilization ratio for it. So you can hover the mouse over the results, and you will learn more about all these inputs, okay. You can also learn what is the total force developed in the rebar. That is very useful. And this is limit force in the rebar. Okay. Now for the serviceability combinations, now you can click over the crack width. So we have a way um, to get the results of the possible cracks. Okay. So you can activate this. The software will analyze the possible cracks on the unreinforced areas, and then you can set up a limit. Some codes, they are giving you a limit for a crack because it's not that straightforward to calculate using traditional calculations. Sometimes they are just providing the minimum requirement of a steel reinforcement to cover the cracks, but we can actually calculate this, the crack width, and then you can set up a limit if you have that. Okay, so with that, in this case, the crack width is not passing, but this is depending on this value that we have here. Then for deflections, it's something similar. When you're using a strut and tie, it's kind of tricky to get the deflection, right? So in this case, we can get the deflection in this structure, and then you'll input this limit. For AASHTO, they have some deflection limits for service load combinations. So some of them, it can be like the length of the beam divided by 1000 or 800. So you can come here and input this value over here. And then you can look at the deform shape. These results, the deflection and crack width, can be only seen for the service combinations. Okay, so that's why you cannot click over the C1 combination, because this is for an strength check. However, I have a trick to show you. If you go to the auxiliary results, it doesn't matter if it's a service or a strength combination. You can look at the deformations here. So now you can look at the deformation of the combination number one, which is a strength. Like the deflection is one result. That deflection results or limits are based on service combinations. But if we're running FEA, we can have the deformation of both combinations. And this is very helpful to see if the structure is deforming as you are expecting. So this is kind of a sanity check. But remember, go to the auxiliary results to see the deformation of the strength combination. Okay, so once you're fine with these results, you're okay, then you can jump into the report. And this is something important, right? So you can come here and generate your detail report. So you select detail, and then you can add some information in these options. I can add the code and calculations assumptions, and then the theoretical background if it's the first time that you're delivering this report. Now, as in any other report, you'll get all this detailed information, geometry, all the loads that were applied, the reactions. You get this nice scheme of reinforcement. Then you'll get the strength results. Another cool thing is that we are providing bill of materials. So this can be included in the PDF report, or you can also click over this bill of materials report. You generate this report, and then you can export it to a CAD file. Finally, I wanted to talk about the third model that we prepared for this presentation, and this is a cross-section of the ledge beam. right? So remember that the objective of this model is to design the shear reinforcement. The way I model this section is using a wall member. I use the polygon option and then I input the coordinates of the shape. So that is one option that you have. The other option is to import a DXF. So you can draw that in your favorite CAD software and then you can bring that shape into detail 2D. Then the other important part of this model is the thickness. So the thickness will be determined by the formula that is presented in AASHTO for when you design the shear force for the beam ledges. So you can use this formula and then that will determine the thickness of your wall, right? And that is basically what is presented here in this example. So I was using this first beam line and I'm using 62 inches for the thickness. So that is for a correct development of the stresses in this model, right? So you can look at this 3D view and that will be the thickness. This bearing path, it was modeled as a bearing plate, and that is how I apply the forces within those bearing plates. So I apply them as a point load, okay? And then similar to what we did before, we created the combinations and we follow the same process. Going to the tools, see the topology optimization, you can see the stress fields, so you can see the tension and then the compression forces over here. And then an important trick here is to model the supports as a patch support. If you click over the new model entity icon, then you will see that patch support. The interesting thing of this support is that you can model it within that wall section, and then when you're creating the rebars, then you interconnect them automatically. Okay, so this is how it's going to be supported. It's going to be supported through, let's say, this uh, vertical reinforcement here, and then we want to see how the stresses and then the shear force is developed over here in this area. Okay, so those are kind of the tips and tricks for the modeling. Then if we look at the results, then you will get similar results to what we were showing before. Okay, so now let's go back to the presentation. All right, let's summarize the key points of this demonstration. So you saw that with topology optimization, you can verify and prove your strut and tie models. Also, you can comply with AASHTO specification for bridge concrete details. So you saw that we have multiple sample projects available in the application, and also you can start from scratch, right? Like I did with this beam frame. Also, you can design for strength and service combinations, and we're going to check 5 limit states. The first one is the concrete compressive strength. The second, steel reinforcement strength and the development length of this reinforcement. So that is equal to anchorage in our application. And then for the service load combinations, you can check the flexion and crack width, right? And finally, the almost the most important part of this design is to deliver a complete calculation package, including bill of materials and CAD details. All right, well, let us know if you have questions or if you want to start using this application. It's available for a trial version, so make sure you go ahead and download and start complying with AASHTO.
All right, Andrea, thank you very much for that great example that you just provided for us. So to wrap up today's webinar, I just want to give you a quick overview of what's new in version 26. So let's go ahead and get started. First up, the checkbot 3D scene has been improved to make navigation smoother, selection clearer, and the overall experience more intuitive whenever you're managing different projects or large-scale projects that might contain a lot of connections. In this case, you will be able to group them, assign different connections, and if you want to make your own group of connections or just delete connections that are non-relevant, you will be able to do all of this in checkbot. Next, we have what is called utilization ratio prediction for connections. So with this, we are excited to be releasing new templates for the steel connection application. And these new templates will be able to predict the utilization ratio as you make changes to your connection. So if you're adding or removing reinforcement, we will be able to predict that utilization right away. Third, the Detail 3D got several important updates. You now have anchor checks built in, so you can verify anchorage directly within the 3D model. There's also failing member explanation feature, which is a huge help for troubleshooting. And surface support reactions are now available. So this is to be able to give you better insight into how the loads transfer into your supports. Fourth, the Detail 3D now updates directly from the connection application. So if you make changes within your baseplate workflow to a connection, those changes can flow directly into your Detail 3D model without you having to rebuild from scratch. And finally, version 26 now provides a complete solution for your embedded plates. So now we will be able to let you handle your design from end to end to be able to have a unified workflow environment. So you could start in the connection application, but if your anchors fail, you know that now you can send your results to detail to be able to analyze that with reinforced concrete. And I know there was more than plenty of information that we covered for today. And so that's why we created a toolkit for engineers where you can find all of this information and more related information all in one place. It's all now available in our website and it will be attached to the presentation slides. We also have a new ish shop that is out now. So if you want to go ahead and check it out, that will also be available. And also don't forget to subscribe to our connections newsletter in LinkedIn. You will be able to get case studies, webinars, tutorials, and all the great news that we have here within our software. So now we can go ahead and begin with the Q&A with a couple of minutes that we have left.
All right. Thank you, Johan. So I am reviewing some of the questions you put here. One common question that I saw is that if AASHTO is going to be implemented in the steel applications. It is on the radar. So if you have some specific cases where you need to use AASHTO for steel connections, it is super useful for us if you share that information. So if you can send us an email to office@ideastatica.com, or if you're a user, just submit a case and explain to us where you're using AASHTO and for what cases. That help us to push it through development. So that was one question. Then there are other questions related to the models, like the beam type of model and then the wall type of model, which is more detailed, let's say. Um, so my recommendation is that you go through this toolkit. I put it on the chat, and also you have this presentation available, so you can go through that link that it says bookmark it now. So if you go there, I have the three models there, so you can download it, and then you can also see the report, and you can see how the loads were modeled. Like one of the questions was that how the loads were applied in the beam element